So, I think we are going to start pretty soon. As I said, on a Friday afternoon, I don't know if we will have many outsiders joining, but I will anyway share the recording of the event. So, for who have joined just right now, we are going to start our event for the World Day of Glacier and the World Water Day, called Fingerprinting Glacierized Catchment, How International Cooperation is Advancing Our Understanding of Hydrological Processes to Adapt to Changing Climate Using Isotopes. First, I'm going to introduce the International Atomic Energy Agency. It's an agency that was established in 1957 by the United Nations as the World's Atom for Peace organization. The IAEA is an affiliated agency within the United Nations. Since November 2024, the IAEA has been comprised of 180 member states. The IAEA is supported by over 2,500 multidisciplinary professionals. The IAEA's mandate consists in three pillars: science and technology, safety and security, safeguard and verification. Inside science and technology, we have the objective to offer cleaner water accessible to more people and improve water resources management. The isotope hydrology section, working on isotope hydrology, is included in one of the 6 departments of the IAEA and comprise above 30 staff, professional staff and laboratory technicians, and is responsible to bring forward all the projects related to resources management in member states. Isotope hydrology section has different roles. For example, we do coordinated research project. We have a program that consists in global monitoring network. We do capacity building and training. We have technical cooperation project, and we support laboratories in all the member states. In the area of CMPs, Coordinated Research Project, this year, for the year of Glacier, we are working on understanding hydrological processes in glacierized catchment under changing climate using isotope-based methodologies. This idea of this CRP was first brought by a consultancy meeting where different scientists talk together to understand better the issue related to glacierized catchment. We realized that glacier retreat is a serious threat to water availability and socioeconomic activities. Changes in the cryosphere increase the probability of mud flow, landslide, and glacial lake outbursts, floods. We don't really understand yet the contribution and storage of glacier melt in surface and groundwater. Based on this, we have also realized that glacier retreat is of international concern, and member states are particularly interested in the theme of glacierized catchment, as we can see that we had discussion during the COP28, the COP27, and the COP29 related on the topic of glacierized catchment and glacier retreat. The proposed activity through this coordinated research project is to define hydrological end members and establish a protocol for a sampling program. We will establish monitoring network, initiate development of novel tools like atmospheric water vapor, AI model, integration of open access data, etc. The idea is to develop and implement the use of isotope hydrology in cryosphere. We would like also kindly mute yourself, please. Okay. The next proposed activity through this coordinated research project is to quantify isotopic values of the selected end member and select additional tracer. We will apply radioactive environmental tracer to date ice layer and quantify contribution of ice melt to runoff. We will share and exchange the knowledge and expand the knowledge to other isotopes like tritium, carbon-14, etc. The overall expected outcome of this coordinated research project is to have more experienced participating member states. We will broaden the scope and applicability of isotope-enabled hydrological models. And the final goal is to better understand the complex water mixing processes in glacierized catchment for optimal water resources management. After our first coordinated research meeting, we defined some activities that are necessary to understand these processes in glacierized catchment on an international level. And working together as a group will allow us to make a capacity review. The IAEA can assess the available infrastructure and determine areas where further support is needed. We can exchange reference material, provide capacity building opportunities for knowledge exchange. We will, for example, make courses in the Spanish knowledge to increase access to isotope hydrology in Spanish-speaking countries. We will coordinate sampling effort, and we will have joint conference participation and joint publication. The group present today from the CMP participant is going to present their work and how isotope hydrology is important to understand a different study area in different regions. We will first start with Canada, and our colleague Jani is going to present her study area and how isotope hydrology can help us understand glacierized catchments.
Thank you, Melanie. Yeah, we start with Canada. Actually, this is like an alphabetical order, so there is no other reason why I'm the one starting. So, I'm Janie Mars-Dufresne. I work at École de Technologie Supérieure in Montreal. Our team is all based in Montreal, and we actually work in Yukon in the St. Elias Mountain. So if I use my mouse, can you? No, you don't see the mouse on the screen, right?
Please,
Okay.
no, we don't see the mouse. And also, please let me know when I should press next. Yeah.
I have only one slide, so there's no
Okay.
need to. Yeah.
Okay.
Okay, so I'll try to guide you over the slide with just my voice and no pointer or mouse. So on the top left part of the slide there, you see a map. This is where we work. You see all this large glaciarized area with very big glaciers. This is the St. Elias Mountains. And for our work, we actually work in the least glaciarized area on the side of it, which is smaller systems, small glaciers. And why do we focus on this part is because these systems are deglaciating very fast. So smaller system, this is the focus, like the zoom map, the B map you see. There are many small glaciers, and these ones are feeding a stream or a creek called Grizzly Creek or Charshataga. And we focus on one sub-catchment of this small catchment already. And what's interesting in there is that there are many cryospheric components all merging into one spot. So this is the figure or the picture, I should say, you see on the right. The larger glacier is back on the back of the image, and the smaller glacier that we or glaciarized catchment that we study is the one coming from the right-hand side of the picture and flowing down this small valley there and transitioning into a rock glacier. So this rock glacier there was our first interest in this system, and we thought, okay, let's try to quantify how much meltwater is coming out of this rock glacier. Actually, we cannot really do it because all the very tiny springs that are coming out of this rock glacier represent just few liters per second. So we were like, oh, what's going on? How is this rock glacier interacting or contributing to the hydrological system there? And we decided to use stable isotopes of water combined to radon 222 activities to understand what is the origin of these very small springs or groundwater resurgence that we can see there. And depending on the season, we actually see two groups. So this is the down left hand side graph that you see with the deuterium and oxygen 18. So based on the isotopic signature, we can clearly differentiate between the springs that are from glacier melt and the ones that are from precipitation, say rain in summer or snow melt in early summer or late summer. So this tool or isotope hydrology there combined with radon 222. So this is the second graph there. We did some measurement in the Charashataga River, upstream the rock glacier and downstream the rock glacier, and we saw that some of the springs that are in yellow there on the graph have important radon 222 activity. So it was an indication for us that this rock glacier is actually acting as constraining the surface water flow, and it acts as a way or a transition where very shallow groundwater can then make resurgent and contribute again to the flow in the stream. So it was interesting to see that within just a few hundred meters, we had this many small contribution to the stream, and with the different physical chemical parameters and concentrations in iron that was evolving due to this interaction between surface and groundwater. So yeah, this is in 5 minutes the work we are trying to do, and it's still ongoing. Thank you.
Thank you, Jenny. I will pass to the next participant. So unfortunately, our participant from Chile cannot be here today, so our colleague Sarah will present for him.
We don't hear you, Sarah.
We don't hear you, Sarah.
How about now?
Yes, thank you.
Yeah. You would think that after 5 years. Okay. But now it works, I guess. Melanie?
Yes, we hear you.
Okay, perfect. You would think that after 5 years, but no. So as I was saying, the counterpart from Chile, Francisco Fernandoy, provided me with a text that goes along with his slides, which I'm going to read to you. He starts off by introducing his study area, the Andes Mountains, which are referred to as very important water towers because of their crucial role in supplying water to a population along the 7,000-kilometer long stretch from Venezuela to southern Chile. These mountains provide water to over 75 million people within the region and also to an additional 20 million people further downstream, according to the UNESCO. Chile is in South America the third largest economy. Very important part of their economy are mining, industry, and agriculture that form the backbone of this country's economy. And most of these activities rely heavily on freshwater resources that originate in these mountain areas, especially in northern and in central Chile, where about 70% of the population lives. The high mountain regions of the Andes, meaning everything that's higher than 3,000 meters above sea level, these are particularly important as they store fresh water in the form of snow and ice, which is then gradually released during warmer seasons. And this ensures that there is water available also during dry periods. However, in Chile, there has been an extensive drought for more than a decade now, which is severely depleting its natural water reserves. And many glaciers in the Andean Mountains have already reached what is called peak water, meaning that their meltwater contribution have peaked and will from now on continue to decline. After the IPCC RCP 8.5 scenario, it is indicated that a significant decrease in precipitation of approximately 30% by the second half of this century will further exacerbate the water scarcity in this region. Next slide, please. Attributing water sources in active geological settings like the Andes Mountains, it's a very complex task. Active tectonics, lithological variability, and water reservoirs make identifying water sources especially challenging. However, the accurate attribution is very crucial for effective water management planning, especially in the face of prolonged water deficit risks. As part of our CRP project, Francisco and his team, they will focus on two different key watersheds that have been partially studied in previous research. One is the Aconcagua River Basin, which is one of the most important river basins in Chile because it supports about 12% of the country's agricultural activities. And it is also hosting some of the largest mining operations. So their approach will emphasize on high spatial resolution data at the sub-basin level to improve water source identification. Next slide, please. Additionally, they will include a second study area, which is the Limari River Basin, with a particular focus on the upper Rio Grande sub-basin, an area that is rich in permafrost and glaciers. This basin is located at the edge of the semi-arid Andes, making it particularly vulnerable to climate change and water scarcity scenarios. This basin is one of the most important regions for agricultural activity in the northern part of the country. Last slide, please. So in previous studies, they could successfully show that the use of natural tracers, such as water-stable isotopes, paired with electrical conductivity in surface and groundwater samples, is a valuable tool for water source attribution and quantification. By combining natural tracers together with statistical models, they identified a clear pattern that demonstrated that common natural tracers serve as a unique fingerprint of water sources. During the most recent prolonged drought in the last 10 years, they detected a significant contribution of cryospheric water reserves, such as coming from glaciers and permafrost, to the regional runoff, and an input that had not been previously quantified. In high altitude areas, cryospheric contributions accounted for over 50% of total runoff under dry conditions. This initial assessment was conducted at a regional scale during a prolonged drought period. And they now, during the CRP, aim to test this hypothesis under different meteorological conditions and in a different geographical setting, while also improving the spatial resolution of their study.
Thank you, Sarah. Now we will have a presentation from Tao Pu from China. Tao, do you hear us?
Yeah, I'm here. Can you hear
Okay.
me?
Yes, we can
Okay.
hear you. Let me know when
Uh,
I pass your slide. Should I start with the first slide?
Yeah, to next slide, please.
Okay.
Okay, thank you. I'm Topu from China, and here I'd like to introduce our projector tracing the hydrological processes in glacier catchments of southeastern Tibetan Plateau using multiple isotopes. Next slide, please. Yeah, and this is our study area. We have three catchments. One is located in the mainly snow mountain, and the catchment is Mingyong catchment. It's a small little glacier catchment, and we also have two catchments in Mountain Yunong region, and yeah, one is Baishui, a little glacier catchment, and another is Yangon catchment. Next slide, please. Yeah, and here I want to introduce our background. We know that the Tibetan Plateau is regarded as the third pole because there are so many glaciers located on the Tibetan Plateau, and we found that most of the glaciers are experiencing rapid retreat. So there are many temperate glaciers in the southeastern of Tibetan Plateau, and these temperate glaciers are more sensitive to climate change. So we want to know how does the glacier change affect hydrological processes, how this meltwater recharge water. So this is what we are interested in. Next slide. Yeah, and here we want to use isotopes like oxygen and hydrogen isotopes to trace the recharge of meltwater to groundwater and surface water. And we also want to use radioactive isotopes like radon, like sulfur 35 to trace the hydrological processings in short time, and we also will use carbon or tritium to data the age of groundwater. Next slide, please. And this is our objective. Firstly, we want to know the isotopic compositions of different water bodies in the glacier catchments. We want to know their controlling factors, and also we want to estimate the contribution of meltwater to surface water and groundwater using isotope isotope as tracers. And based on this, we also want to study the effect of climate and glacier change on water resources in glacier affected regions. Okay, next slide, thank you. And this is our monitoring plan in Mingyong catchment. In this catchment, we focus on the recharge of meltwater to surface water. We observing different observing what isotopes, ions, and also meteorological and hydrological parameters in this region. And we get samples of different types of waters like groundwater, precipitation, meltwater, and river water. Yeah, next slide, please. And in mountain Yunong, in Yunong region, actually we are mainly focusing on the recharge of meltwater to groundwater because in this region there are many springs flowing out of the ground. But in these years, many springs, for many springs, there were no water flowing out of the spring. So the local government and we also focus, we want to know why this the water level began to go down. And for this catchment, we have different types of water sampling site. We also want to use ions, water isotopes, and different isotopes to do this research. We want to know the relationship between glacier change and snow change on snow melting and groundwater. So we want to know the relationship between groundwater and the cryosphere. Next slide, please. And we expect we could collect data, especially isotope data in different water bodies in glacier catchments in Tibetan Plateau. We also want to quantify the recharge of meltwater to runoff and groundwater. Also, we also want to know the impact of climate change, glacier change on water resources and hydrological processings. And these are our research team, include Professor Kong, Dr. Shi, and we hope that we could publish related papers and scientific report. Yes, that's all. Thank you.
Thank you very much, Tao, for this insightful presentation. We are going now to Hungary with our counterpart from Hungary. Mariam?
Thank you. Thank you very much. I'm Marian Temovsky. Please go to the next slide. From the Institute for Nuclear Research in Debrecen, Hungary. Our project is a bit different in the way that we are looking into to understand the natural variation of an excellent isotope tracer for hydrology. Can you go to the next slide, please? So we are looking into the radioactive isotope of hydrogen, tritium, which is used as a tracer in isotope hydrology, an excellent one, allowing to determine age of young waters. What we're trying to do is to understand what are the natural, what are the controls on the natural production variation of tritium, in which case we can improve its applicability in isotope hydrology. The next slide. So, few words about tritium. So, aside from the fact that it's a naturally produced isotope, there has been a very large contamination of the atmosphere with the anthropogenic tritium content, which was produced by thermonuclear weapons testing mainly in the 1960s. However, due to its short half-life and radioactive decay, tritium content has decreased, and it's approaching some steady state level. But there is a question: are we really back to a natural level or not? Can you go please to the next slide? And on another side, there is a question about the production of tritium in the atmosphere, the natural production, and the question of whether the solar cycles are very actually influencing the natural variation, as a study that we have been working on. So what we're trying to do, can you go please to the next slide, is to look into the ice cores, so the glaciers, to obtain an archive of past variation of tritium before this contamination which occurred in the 1960s. However, there is a catch. We are kind of running out of time from one aspect, of course, because glaciers are melting. We are losing ice. But on the other hand, due to the short half-life of tritium and the possibility to precisely measure its concentration in a 100-year-old ice, we are kind of running out of time that in 10, 20 years, this window of before the 1960s will be too low the concentration of tritium left to be able to be precisely measured. So we are kind of on a global hunt. Can you go please to the next slide? We are on a global hunt to provide as many as possible reconstructed records of natural tritium concentrations in ice. We have worked on the Swiss-Italian Alps drilling glaciers. We have collected cores from colleagues from the Tibetan glaciers. The next slide, please. We have drilled in Greenland at the East Creep site. Next slide, please. And within the project, we are planning in the near future to work to collect more samples from Svalbard, from Grigoriev ice cap in Kyrgyzstan, as well as from ice caves in Central Europe. So briefly, this is a presentation of our project within this year. Thank you very much.
Thank you, Marian. Now we are going to Kazakhstan with Serena.
I hope everyone see me, and
Hi,
I
Serena.
would like to ask you to move to the next slide. So moving to Kazakhstan, I would like to present the project within the RCP we will carry on. It's in two glacierized catchments, Ulken Almaty and Kishi Almaty, which is located in the glacierized mountains, and most of the water coming to the river coming from the glaciers to these rivers, and these rivers provide a crucial role for the agriculture downstream community. However, the idea and motivation of our project was based to understand the connection between the cryosphere and the groundwater, because about the river itself we have at least some information, but about the groundwater the information is very limited in the region, although the groundwater provides around 50, sometimes even more percent of the supply water of the bigger cities. Next slide, please. So the main questions which we decided to have a look during this project is how the groundwater connected with the cryosphere, and how the cryosphere affecting on the groundwater availability, what are the pathways from the cryosphere to the groundwater is, what kind of the end members and source of the cryosphere contribute to the groundwater. And the last question, which we would like to answer at the end of the project, is what the backward response of the groundwater to the stream flow. As a data collection, we need to collect all sources, or as they called end members, which include glaciers, precipitation, stream flows, and as well groundwater wells. In additional data collection, which will show up what is going on in the region and how the climate change will affect on the different kind of sources, we need to collect the meteorological data and also hydrological data, which will include the precipitation, temperature, and the runoff. For the analysis, we've picked up three main things. Is analysis of the stable isotopes, which will include the deuterium and oxygen-17, oxygen-18 as radioactive isotopes. We pick up the tritium, which allow us to evaluate the dating of the groundwater, and as additional tracer, which allows us implement the mixing model, is measurement of physical parameters of the water, is electrical conductivity, pH, and total dissolved solid. So for the data analysis, we pick up the statistical methods which called the Bayesian, and also the another statistical model, which is end-member mixing models for the distinguish the contribution of different sources, as well as we will use the GIS technologies for the mapping of our sampling and how they related in space. And finalize our research, we would like with some conceptual model, which will show up the connection between the cryosphere and the groundwater. And then the picture you see from the project which already carry on, we see evidence that the groundwater recharge system has a different paths of the recharge of the water from the cryosphere, which gives us hope that we will apply these methods. So next slide, please. And why the isotopes? I just would like to explain that the isotopes is a unique tools which allow us to distinguish the fingerprint of different sources, and then to distinguish this contribution of different sources to runoff, groundwater, and either in precipitation, if you are looking on the connection of the evapotranspiration and the precipitation. So the isotopes is powerful tools which we would like to apply in this project. Thank you so much.
Thank you, Sarina. Thank you so much. We will now move to our counterpart that is based in Romania. Hello, Aurel. Nice to see you.
Hello. Hi, Melanie. Thanks for inviting me. So I will go quickly through our ideas. First of all, most of the studies are related to presence of ice in caves. It's because I work at the Spatial Institute that I like doing these things. But the geographic area is not restricted to Romania only, but several other countries in Southeastern Europe. So basically, we are studying 3 different types of ice. We are looking at perennial ice in caves. We are looking at rock glaciers, mostly in Romania, possibly also in Bulgaria. And then we are looking at small glacierized in Bulgaria. So the first type of ice that I'm looking at is ice in caves. You can see it in the next slide, the 2 different types of ice that I'm studying. First, we have ice formed by the freezing of water. On the left, you see an example from Scărișoara ice cave. This is a true glacier. It has all the characteristics of a glacier. It is formed by the freezing of water. So this type of ice accumulates in caves in Central Europe at lower altitudes. In the high mountains of the Balkan Peninsula, in Greece, in Croatia, and also to some extent in Slovenia, we have a different type of ice caves or caves with ice, in which ice accumulates by the continuous metamorphosis of snow. And you can see on the right an example from Cherna Ledenica. The bottom line of this type of ice accumulation is that we have a layered glacier with each layer consisting on 1 year, and it can be very nicely and precisely be dated with radiocarbon, so we can get a very good chronological control for these ice deposits that can be used to understand the isotopic composition of ice. The second type of ice is rock glaciers, mostly in the Carpathian Mountains. We have about 50 rock glaciers, small in size, but nevertheless, they are contributing most of the discharge to the rivers downstream. And the third type of ice, as you can see in the next slide, is the small glacierized in Bulgaria. These are some very interesting ice accumulations you can see in panel C on the lower left. So they are mostly fed by snow from higher altitudes through avalanches. So they would not survive at this altitude, considering the weather and the climate at that altitudes where they are located now. It's too wet. But most of the snow is being fed from above, from altitudes which are something like 400 to 500 meters above. Why we are interested in these is first because they are indicators of changing patterns of precipitation, and second, it seems based on preliminary data that they are recharging some springs located at the foothills of the mountain. So this is a limestone area, and all the water is drained to caves to the bottom of the mountains, emerging through some springs. So on these 3 types of glaciers in the Balkan Peninsula, we are looking at 2 different objectives, and you can see in the next slide. First is the reconstruction of past climate variability in Southeast Europe. I'm looking at oxygen and hydrogen isotope ratios as indicators of winter air temperature, the ratios of light to heavy isotopes, heavy to light, and also I'm looking, and which is the most important part, I'm looking at the deuterium excess as an indicator of moisture source. And the second objective is to see to what extent these rock glaciers and glacierets are supplying water to rivers downstream. And we have some preliminary data for both of these objectives. On the next slide, you will see some data from ice caves in Romania. So we are using, again, as I said, oxygen and hydrogen isotopes as proxies for winter air temperature and deuterium excess. The thing that I'm mostly interested in is the deuterium excess. You can see on the fourth line from the bottom, the brown line. You can see a change in the deuterium excess throughout the Holocene, from lower values in the early Holocene to higher values in the late Holocene, which indicates a change in the moisture source from the Atlantic towards the Eastern Mediterranean. And the goal of this study is to use a network of such records from different parts of the Balkan Peninsula to see the spatial difference between the different sources of moisture. The idea is to be able to reconstruct for the Holocene, or maybe the late Holocene would be better because we don't have such long records, how the moisture sources have shifted in response to large-scale atmospheric circulation pattern changes. So we hope that then we can use this for the prediction of future changes. So this is when it comes to isotopes in cave ice, and when it comes to isotopes in rock glaciers and also in glacierets. We are looking at springs that are draining both rock glaciers. In the figure, you can see them in blue, and springs, let's say normal springs that are draining areas free of ice. And these are you can see that the two different types of springs are very neatly separated in this delta O18, delta 2H space. What is also interesting is that the values are higher than what we know that is the isotopic composition of ice based on 2 samples only, but it is also higher than the isotopic composition of winter snow. So we believe at this point that what is happening in this area is that during the spring, we have a refreezing of the water inside the rock glaciers. So these rock glaciers are not just relics of colder climate, but they are continuously storing water and releasing it throughout the year. And then they are contributing continuously to the discharge of the rivers. However, if the ice core is being lost, as we think that is happening now, that means that the storage capacity of the rock glaciers will be also lost, and all the small rivers downstream will become dry in the next years or decades. So this is what we want to study using isotope hydrology for the rock glaciers. So yeah, that would be my presentation. Thank you very much. This is the end of it.
Thank you, Oren. Thank you very much. Now we are moving to Slovenia with Polona. Hello, Polona.
Hello, thank you, Melanie, and hello, everyone. So my name is Polona Vreča, and I will present activities performed in Slovenia, a Central European country squeezed between the Alps, Mediterranean Sea, and Pannonian Basin. And one fact is that our country is very small, only about 20,000 square kilometers, so that you can hardly see the yellow dot in the map on the right. But our country is very diverse in morphology, geology, also climate conditions. And due to carbonate bedrock, karst topography is a typical phenomena. Next slide, please. So in Slovenia, the last glaciation reshaped approximately 9% of the country. Only 2 glacial remnants remain visible, namely the Triglav and the Skuta Glacier, presented in top figures in the slide. In addition to that, there are more than 11,000 caves registered in Slovenia, and more than 200 of them have permanent ice. However, we don't know exactly how much ice is actually stored under the ground. So the glacier and ice cave deposits are situated at relatively low altitudes and are significantly impacted by the climate change. As you can also see in the photos upper left how the Triglav Glacier actually shrank, and in 2023 just fall apart into two small patches. Luckily, we managed to take some ice core samples just before that happened. And afterwards, we focused more on the ice caves, as you can see from photos below. So next slide, please. The cryosphere investigations, so the isotope cryosphere investigations are relatively rare in Slovenia and also quite new field for me personally. So the objectives of our study are to synthesize the previous results, assess the data obtained during the investigations performed 2 years ago, and then also to collect new data, particularly on isotopic composition of ice cave deposits. And two very detailed profiles were already sampled, and analysis of those two are already, so the isotope data are more or less already available, but other parameters will also be measured, so it will take some time to get all this data together. So finally, of course, with project partners, we would like to prepare some guidelines, particularly for water managers. Next slide, please. We perform investigations at two institutions. So there is a cooperation between the researchers from Josef Stefan Institute and Geographical Institute of Anton Melik. And the results that we will get will definitely deepen our understanding of Slovenia's climate history, and also help to define the cryosphere isotope end member, which was not defined in the past. By integrating the findings with other existing isotope data from water cycle components like precipitation, snow, snowmelt, surface water, and groundwater, the project will provide very important information for water managers, this information will be used then to better predict and also adapt to hydrological changes in the Sava River catchment, which is the vital water source for Slovenia. Thank you very much.
Thank you, Polona. Thank you very much. We still have two presentations left. We are going to the UK, who is also working in Central Asia, and Zarina will present before finalizing this session with Uzbekistan. Zarina, please, the floor is yours.
Yeah, I'm inviting you again, moving to the Central Asia, and I'm presenting behalf of the Professor Maria Shakidanova and Professor Andrew Wade, University of Reading. And this project, which started in 2019, has a very extensive sampling program located in 6 catchments in Central Asia. It's 2 catchments in Kazakhstan, 2 catchments in Kyrgyzstan, 1 catchment in Uzbekistan, and 1 catchment in Tajikistan. So next slide, please. And motivation behind of this project was that the Central Asia is a hotspot of the climate change, and the water resources becoming more and more crucial issues for the region. As far as I said before, that the most rivers coming from the cryosphere and then feed into the downstream communities, uncertainties related to the water resources availability in the future becoming more and more important for the water management and different kind of adaptation related to that. According to the different hydrological modeling, we will have the peak of the runoff by some models as a mid of century, by some models in the latest years of the century. But after this peak, we will have decrease in runoff. And to evaluate how it will affect on the community and how we should adapt and what we have to do, we need to understand the formation of this runoff. And the aim of this project is to quantify the contribution of the different water sources to the runoff, including cryosphere members. And you see on the plot with the different catchments, sampling points, which is covered different elevations and different kind of water sources. Measurements itself cover extensive sampling of the different components of the cryosphere, such as snow, glacier, ice, rock glacier, permafrost, as well as the sampling program includes the groundwater sampling and also the precipitation samples. Already over the 9,000 samples collected and analyzed for the deuterium and oxygen 18. So as you can see, in a cryosphere part was also collected a lot of samples related to different cryosphere components. And based on that, you see on the figures, clear distinguish between the different cryosphere components, which allow us to apply the isotopes for the calculation of the contribution different water sources. Next slide, please. As I said before, why we want to do it, because the adaptation strategies will depend on different contributions, different components and different contribution of these components, because if it's, for example, renewable components like rain or seasonal snow, we don't need to be very quick in our actions and adaptations because we still will have it. But if it's we have a main component to contribute in our river system is the glaciers. As the glaciers retreat very fast, we need to act much quicker than with the renewable components. So the idea is to know how we should act by the end of century. So on the picture, you see the preliminary results of the application of the Bayesian mixing model for the quantification of the contribution different components of the cryosphere, precipitation, and the groundwater. On the first two top part, you see the Ulkenalmati and Çankırı, which is the northern catchments, and you see that the contribution and glacier melt is dominated in that catchments, although in Ulkenalmati we have also high contribution of the groundwater. When we move into the southern part, the contribution of the glaciers change to the contribution of the snow, and the domination of the snow contribution in the Chirchik is obvious and on the bottom panel of the pictures. So this is main idea to improve this understanding, to use isotopic analysis and use isotopic tracers with additional physical parameters of the water, and then to provide adaptation strategies for the policymakers. Thank you so much.
Thank you, Sarina. And we will finally finish with traveling around the world with isotopes and ice with Uzbekistan and Bahrain.
Hello, everybody. My name is Bahret Danishonov. I am working at the Hydrometeorological Research Institute. The title of our sub-project is Evaluating the Impact of Climate Change on Glacierized Catchments in the Chirchik River Basin using Advanced Isotope Hydrology Techniques. In Uzbekistan, we have two river basins. One of in south part of Uzbekistan is Kashkadarya River Basin, and second is in the northeast part of Uzbekistan is Chirchik River Basin. Our work may be some continuation of the what was done by the Uzbekistan team with UAK team on investigation of Chirchik River Basin and glaciers, and we plan to collect samples from this Chirchik River upstream, the Aigaing River Basin. Next, please. And project objectives is using of the isotope technology to develop and apply for dating and mixing of water sources using stable isotope radioactive isotopes, and also using of modeling to enhance the analytical accuracy of isotope-enabled models to improve the differentiation of water budgets, and also water sources characterization to determine the feed of water sources in Chirchik River Basin, and so to assess the climate change impact to the water resources in this Chirchik River Basin. Why it is important for Uzbekistan? Because Chirchik River is main sources of water for the agriculture, industry, and for drinking water, especially for Tashkent city, is capital city of Uzbekistan. So next, please. So we plan to sample water. Firstly, precipitation samples in the meteor stations in the mountain, also in downstream. We already maintained 4 Palmex samplers in the Aigaing, Maidantal, Pskem meteor stations, also in Yangul meteor stations. And also we are planning to sample stream water in the Chirchik River Basin in the upstream Aigaing in Maidantal catchments. And also we are planning to do 2 field walks in 2025 and 2026 to the Barkrak glaciers in the Aigaing catchment to sample of ice, snow, and other water samples. And also we are planning to analyze water samples for the and precipitation samples for water stable isotopes is deuterium and oxygen 18. Also, we will try to analyze for tritium also. Also, we will conduct additional measurements of water and precipitation samples on electrical conductivity, temperature, and pH. And also, we will conduct laboratory analysis of samples for major ions and other tracers. Next, please. And expected outcomes of this research is to determine this isotope distribution, in detailed mapping of the seasonal and spatial distribution of isotopes in precipitation within the catchment, identification of the source of air masses contributing to precipitation in the basin, also to analyze the seasonal isotope fluctuations along the Chirchik River Basin and in its tributaries, assessment of the impact of the anthropogenic activities and evaporation on the isotope variation. Also, to use the isotope techniques, methodologies, and models to identify the contributions of various water sources, precipitation, glaciers, or snow melt, or groundwater to runoff formation in Chirchik River Basin. Next, please. I think so. Thank you for your attention.
Thank you so much. We will now finalize this roundtable with because every participant here worked on a specific project in their area, But with all this data that we are going to gather, of course, we will work together, help each other, but we are also going to have a joint publication. And Sarah will present now, as a conclusion, a very short slide on the output of this database compilation.
Next slide, please.
Okay.
Thank you. So we have just heard in all the case studies presented from around the world, we talked a lot about end members, different water sources in these glacierized catchments. We heard about water coming from glaciers, from glacier ice, snow precipitation. There were some rock glaciers in the studies, springs and groundwater. And so as the first research question of this coordinated research projects, we defined that it would be very interesting to look at the variability of the water isotopic signatures of all these end members in glacierized catchments that contribute to water flow downstream. That contribute to the stream flow leaving glacierized catchments. The methods how to do that is, first of all, gather all the data we have within this group from the various research locations and the data all the participants are collecting themselves, as well as looking at already published peer-reviewed papers, of which so far we have identified around 100 from all around the world. We plan on extracting all this data and grouping it into different regions to see how the isotopic signatures of all these various end members vary from region to region. The goal of doing this work is we want to create a global reference framework that people can refer back to. If they're interested in what is the isotopic variation of a specific end member in a specific region, with the aim to help in water management and those isotope-based methodologies in glacierized catchments.
Thank you, Sarah. So with this, we have finished our side event. Here you can have a list of resources available on the IAEA website on isotopes, isotope hydrology, monitoring, and also for sampling procedure for isotope hydrology. And you can also find more information on CRPs if you are interested to join in a CRP research project at the IAEA. You also have more information on the social media, and I would like to thank all the participants today and the person who have joined online. We will give a minute for questions if there is any, otherwise we will conclude this event today. And the recording will be available soon. Okay. I don't see any hand raised, so I thank you again, every participants of the CRP, for doing this effort today. This event is recorded and it's an output of our CRP. We will keep it as a record of our work. So thank you again so much for joining today and for this nice event.
Thank you.
Thank you.
Thank
Thank
you.
you, Melanie,
Bye.
Thank
for
you.
putting this together
Thank
and
you.
your colleagues.
Thank you,
Thank
bye.
you.
Thank you very much.
Bye.
Nice weekend
Bye.
to all.
Bye.